Welcome to DTH channel, lecture 8 of Atomic and Molecular Physics, Fundamentals of Atomic Spectroscopy. This is the title of this lecture. I am going to present this lecture in the following way: introduction, normal modes of vibration of molecules, electronic spectrum of molecules, harmonic oscillator, a fundamental concept to understand vibrational spectroscopy, and summary of the discussions we are going to have. Our most detailed knowledge of atomic and molecular structure has come from spectroscopic study of the emission, absorption and scattering of electromagnetic radiation accompanying transitions among atomic or molecular energy levels, whereas atomic spectra involve only electronic transition. The spectroscopy of molecules is more complicated because vibrational and rotational degrees of freedom added to the electronic transition of the atoms. In molecule, atoms are there. To understand the atomic spectra, only electronic transitions are enough, but to understand the molecular spectroscopy, vibrational and rotational degrees of freedoms are required. We will be learning that vibrational and rotational degrees of freedom in this lecture. Early observations of absorption or emission by molecules were characterized by band spectra in contrast to the line spectra exhibited by the atoms. It is now understood that these bands reflect closely spaced vibrational and rotational energies augmenting the electronic states of a molecule. So, a complete spectrum of a molecule can be obtained by integrating the electronic transition, vibrational transition and rotational transition of the molecule. With improvements in spectroscopic techniques over the years, it has become possible to resolve individual vibrational and rotational transitions, because individual vibrational and rotational transitions are comprised of many sharp lines spaced together. So, with the advent of new spectroscopic instruments, which is very highly resolvable, can be used to resolve the line spectrum of the molecules. This has provided a rich source of information on the molecular geometry, energetics and dynamics of the molecule. Molecular spectroscopy has also contributed significantly to analytical chemistry, environmental science, astrophysics, biophysics and biochemistry. Atomic properties of the atom and molecule throws enough light to understand the spectroscopic behavior of the atoms and molecules. In this lecture, we are going to learn some fundamentals about the atomic and molecular spectra. The first fundamental concept in the atomic and molecular spectroscopy is normal modes of vibration. All atoms in a molecule is generally in motion according to Heisenberg's uncertainty principle. Heisenberg uncertainty principle connects the position and momentum of a molecule, an atom, a particle. So, position, the product of uncertainties in position and momentum of a particle will be greater than h cross by 2. That is the Heisenberg uncertainty principle. So, Heisenberg uncertainty principle says that no particle or atom or molecule is in rest position. Three general types of motions are exhibited by molecules, which are translational, rotational and vibrational. Translational motion is an external one, rotation and vibration motions are internal one. within the molecule, atoms rotates and vibrates. Translation will take place when the whole molecule moves from its position to the other position and comes back to its original position. A to and fro motion can be executed by the molecule in the translational motion. A diatomic molecule contains only a single motion, while polyatomic molecules exhibit more complex vibrations known as normal modes. A molecule has translational and rotational motion as a whole, while each atom has its own motion. Combination of motions of all atoms gives the molecular motion. That is why it is said that a molecule has translational and rotational motion as a whole, while each atom has its own motion. The vibrational modes of molecules can be either infrared active or Raman active. This infrared active and Raman active property of a molecule can be calculated from the vibrational spectroscopy calculation. For a vibrational mode to be observed in the infrared spectrum, changes must occur in the permanent dipole of the molecule. So, dipole molecules will exhibit this infrared spectrum. Diatomic molecules are observed in Raman spectra, but not in the infrared spectra. The reason for this one is that diatomic molecules have no permanent dipole and therefore one single vibration. You know, dipole means two equal and opposite charges separated by a very small distance is called a dipole. So, atoms inside the molecule will have a dipole property, some atoms will not have the dipole property. An example of this would be oxygen and nitrogen. So, dipole property of a molecule plays an important role to distinguish that molecule as infrared active or Raman active. However, unsymmetric diatomic molecules like CN do observe in the infrared spectra. Polyatomic molecules undergo more complex vibration that can be summed or resolved into normal modes of vibration. There are several types of normal modes of vibrations: asymmetric, symmetric, wagging, twisting, scissoring and rocking are the normal modes of vibrations for polyatomic molecules. Next, come to the calculation of number of vibrational modes. How to calculate the number of vibrational modes of a molecule? For that, degrees of freedom is an important one. Degrees of freedom means what? Degrees of freedom is a number of variables required to describe the motion of a particle completely. For an atom moving in a three-dimensional space, 3 coordinates are adequate so that its degrees of freedom is 3. You can imagine a Cartesian coordinate system which has x, y and z direction. If an entity is placed in that Cartesian coordinate system and that entity moves from its initial position to some other position, the movement of that entity can be described using the 3 coordinates x, y, z. So, degrees of freedom for that entity is 3-dimensional space. Its motion is purely translational. For an atom moving in 3-dimensional space, its motion is purely translational. If you have a molecule made up of n atoms or ions, the degrees of freedom becomes 3n, because each atom has 3 degrees of freedom. So, n atoms will have 3n degrees of freedom. This is the very basic concept in calculating the number of vibrational mode, number of degrees of freedom. Furthermore, since these atoms are bonded together, all motions are not translational. Some become rotational, some other vibrational. So, In a molecule, some atoms will exhibit translational motion, some exhibit rotational motion, some exhibits vibrational motion. Then molecules can be classified into two categories based on the arrangement of atoms in the molecule: linear molecule, nonlinear molecule. For nonlinear molecules, all rotational motions can be described in terms of rotation around 3 axes. The rotational degrees of freedom is 3 and the remaining 3n minus 6 degrees of freedom constitute vibrational motion. So, for a nonlinear molecules, that degrees of freedom can be computed using 3n minus 6. For a linear molecule, however, rotation around its own axis is no rotation because it leaves the molecule unchanged. So, there are only 2 rotational degrees of freedom for any linear molecule, leaving 3n minus 5 degrees of freedom for vibration. So, you can calculate the vibrational degrees of freedom for nonlinear molecule and linear molecule. For nonlinear molecule, it is 3n minus 6, where n is the number of atoms. For linear molecule, it is 3n minus 5, where n is the number of atoms. There are procedures to be followed to calculate the number of vibrational mode. First thing, you have to determine whether the molecule is linear or non-linear. If the molecule is linear, then you have to use the formula 3n minus 5. If it is non-linear, then you have to use the formula 3n minus 6 to calculate the degrees of freedom of the molecule, where n is the number of atoms present in the molecule. The next concept in the spectroscopy is reduced mass and wave number. Earlier we have seen vibrating modes, number of modes of vibration, now reduced mass and wave number. This reduced mass is a vital spectroscopic parameter to understand the various atomic and molecular spectrum. In a diatomic molecule, reduced mass is calculated from the equation mu is equal to m1 into m2 divided by m1 plus m2, where m1 and m2 are the masses of each atom present in a diatomic molecule. Then coming to the wave number, number of waves per unit distance of radiant energy of a given wavelength is the wave number definition in spectroscopy. For calculation purpose, this wave number can be calculated or obtained by reciprocating the wavelength. In spectroscopy, the wave number is measured in per centimeter. That means for a vibration 300 centimeter inverse is the wave number, means what it actually says is in that vibration 300 waves are there per centimeter. That is the understanding of wave number. So, reduced mass and wave number. Next, using this number of modes of vibration, reduced mass and wave number, you can explain the electronic spectra of molecules. In the starting of this lecture, we have seen that electronic spectra is purely atomic. Transition between atomic energy levels will give this electronic spectra. Other types of spectra like vibrational spectra and rotational spectra are the transition between molecules, a complex one. Here we are going to see the electronic spectra of molecules. Molecules exhibit electronic spectra from transition between electron energy levels. These electron energy levels are proposed in Bohr atom model. These spectra are more complex than those of atomic spectra, which involves transition between electron energy levels, which typically produce sharp line spectra. Because in atom well defined energy levels are there, but in a molecule all the energy levels of all the atoms should be put together, and the transition between the electronic energy levels in the molecule should be explained. That is why the electronic spectra of molecule is more complex than those of electronic spectra of atoms. The energies associated with molecular electronic spectra, which is typically in the optical or UV region, are much larger than those associated with vibrational spectra. Vibrational spectra energy region will be typically in the infrared region, and rotational spectra energy level will be typically in the microwave region. So, energies associated with molecular electronic spectra are much larger than those associated with vibrational spectra and rotational spectra. This contributes to the complexity of the electronic spectra, since the transition from a multitude of vibrational and rotational levels produce many spectral lines, that is a band of frequencies. Here you can see the energy level of two atoms in a molecule, excited state and ground state. So, in a molecule two states are given here. So, this is obtained by combining the ground state of all atoms in the molecule. This is obtained by combining the excited state of all atoms in a molecule. So, as a whole you will get one ground state for the molecule, then one excited state for the molecule. Transition takes place here. This is electronic transition of a molecule. This electronic transition is in optical region or in UV region. If you take this one, vibrational transition, and if you take the smaller one here, that is rotational transition, we will be seeing that rotational spectra more elaborately in the coming lecture. So, this is the pictorial explanation for electronic spectra of molecules. Then another important concept in spectroscopy is Franck-Condon principle. This Franck-Condon principle talks about the motion of nucleus while exhibiting the spectroscopic property. So far we are discussing only about the transition between energy levels, electronic energy levels. What happens to the nucleus? Franck-Condon thought about that and gave a principle. Electronic transitions are essentially instantaneous. So, there is no time appreciable motion of the nuclei. So, the transition appears as vertical line with no change in internuclear distance. Nucleus is not moving in the transition, spectroscopic transition. This is referred to as Franck-Condon principle. The spectra are strongly affected by the probability that an electron is at a location to contribute to such a vertical transition. That probability is the wave function squared, a quantum mechanical concept. A quantum mechanical concept says that probability of an electron in a wave function is to find the electron in that wave, that is the probability of a wave function. So, like that here the probability is the wave function squared, and at least the lowest vibrational states are approximated by the quantum harmonic oscillator. This quantum harmonic oscillator concept is another important concept in spectroscopy to understand the vibrational spectrum of the molecules. This is the pictorial explanation for Franck-Condon principle. Franck-Condon principle states that there is no appreciable movement of the nuclei. Here this is the excited state of the molecule comprising many vibrational states. This is the ground state of the molecule comprising many vibrational states. So, here you can see the curve position, the concave position is slightly shifted, not a appreciable amount of shift is there. So, with this Frank Condon says that there is no appreciable movement of the nuclei in molecular electronic transition. The probability at any position is approximated by the quantum harmonic oscillator. So, quantum harmonic oscillator, as I said, is another important concept to understand the vibrational spectrum of the molecules. Coming to quantum harmonic oscillator. Schrödinger equation is an important equation in quantum mechanics to understand the properties of a particle. Here electron can be assumed as a particle. If you take hydrogen atom, only one electron is there. Schrödinger equation can be solved for hydrogen atom to get the energy of the hydrogen atom or energy of the electron. This Schrödinger equation can be extended to many electron atom, but it is bit complex one. It requires more time to solve the equation. So, here we will be taking only the one electron system. Schrödinger equation for a harmonic oscillator may be obtained using the classical spring potential, which is nothing but half k x square, then which is equal to half m omega square x square. This half m omega square x square came from the concept of angular frequency. Omega is equal to square root of k by m, where k is the wave vector, m is the mass of the electron. If you square this, you will get k is equal to omega square m. So, that is substituted here instead of k. So, the classic spring potential changed to the form half m omega square x square, where omega is the angular frequency, which can be obtained from the linear frequency by multiplying the linear frequency by 2 pi. Now, Schrödinger equation with this form of potential, this is the potential. So, Schrödinger equation is this one, minus h cross square by 2m d square psi of x by dx square, where psi of x is the wave function used to represent an electron which is in motion. We know fast moving electron or any matter will exhibit a wave like property. So, that wave function of the electron is taken into account here, and this term came in this equation, plus half m omega square x square psi of x, which is nothing but the classical spring potential, which is equal to E psi of x. So, this minus h cross square by 2m d square by dx can be taken as Hamiltonian of the system. So, h psi plus V psi is equal to E psi is the general form of this Schrödinger equation. This equation is taken to understand, to explain the quantum harmonic oscillator. Since the derivative of the wave function must give back the square of x plus a constant times the original function, this is that constant times, this is that original function, the following form is suggested. So, the solution of Schrödinger equation will be of this one, psi of x is equal to c e power minus alpha x square by 2. Substituting this function in the Schrödinger equation and fitting the boundary condition leads to the ground state energy for the quantum harmonic oscillator. This is the pictorial diagram for quantum harmonic oscillator. So, E naught is equal to h cross omega by 2 is the expression to denote the ground state energy level of a quantum harmonic oscillator. This energy expression came from the wave function. substituting this wave function into the Schrodinger equation and substituting all the boundary conditions, we will get the expression for energy of the ground state. The general solution to the Schrodinger equation leads to a sequence of evenly spaced energy levels characterized by the quantum numbers n, principal quantum number. For n is equal to 0, this E naught is equal to half h cross omega. That means even at 0 Kelvin, the atoms are not in rest position, or molecules or particles are not in rest position. That is the very basic physics explained by this E naught is equal to h cross omega. When n is equal to 2, it becomes n is equal to 1, n is equal to 1, it becomes 1 plus half h cross omega, which is nothing but 3 by 2 h cross omega. Like that, in general, you will get the energy value of the nth level of the harmonic oscillator. En is equal to n plus half h cross omega. Here each transitional energy is h cross omega. Then potential energy will be half kx square. This is the quantum harmonic oscillator energy expression. This quantum harmonic energy expression is used to explain the vibrational spectroscopy of the molecule. The wave function for the quantum harmonic oscillator contain the Gaussian form, which allows them to satisfy the necessary boundary conditions at infinity. In the wave function associated with a given value of the quantum number n, the Gaussian is multiplied by a polynomial of order n. Polynomial is a mathematical entity which comes in mathematical physics, which has more components in an equation, that is a polynomial of order n called a Hermite polynomial. The expressions are simplified by making the substitution y is equal to square root of alpha into x, where alpha is equal to m omega by h cross. So, you will get the wave function for the harmonic oscillator. That wave function will be a Gaussian one, will be in the form of Gaussian. That is the understanding from that area. The general formula for the normalized wave function is psi n of y is equal to alpha by pi to the power 1 by 4 into 1 by square root of 2 power n into n factorial h n of y e power minus y square by 2. So, this is the normalized wave function expression. This normalized wave function is obtained from the solution of the Schrodinger equation after substituting all the required parameters. The quantum harmonic oscillator is one of the foundation problem of quantum mechanics. It can be applied rather directly to the explanation of the vibration spectra of diatomic molecules, but has implications far beyond such simple systems. It is a foundation for understanding of complex modes of vibration in larger molecules, the motion of atoms in a solid lattice, the theory of heat capacity. Like that, many more concepts can be understood by the application of this quantum harmonic oscillator. Coming to the intensities of the spectral lines formed by the transition, Beer-Lambert law is used to govern the intensity of the spectral radiation. That Beer-Lambert law is log into I naught by I is equal to epsilon into C into I, where I naught is the incident and I is the transmitting intensity, C is the molar concentration of absorbing species, L is the path length and epsilon is the molar extinction coefficient, conveniently given in the units of mole inverse, centimeter inverse. The maximum value of this epsilon, which is nothing but the molar extinction coefficient in a band, is represented by epsilon max, is a convenient guide to the absorption intensity, although a better theoretical measure is the integrated value over the band. This intensity concept is used to understand the absorption spectrum of any substance. If you are synthesizing or preparing a new material, if you want to know the absorption parameter, absorption characteristics of that material, you can subject that material to UV visible spectroscopy and apply this Beer-Lambert law. So, you will get the absorption coefficient of the material and you can get the band gap of the material. So, the intensity of a transition is governed by selection rules. In this lecture, we have seen early observations of absorption or emission by molecules were characterized as a band spectra in contrast to the line spectra exhibited by atoms. All atoms in a molecule is generally in motion according to Heisenberg uncertainty principle, and three types of motions are exhibited by the molecule, namely translational motion, rotational motion and vibrational motion. Then another important parameter to explain the spectroscopic concept is degrees of freedom, which is nothing but the number of variables required to describe the motion of a particle completely. The degrees of vibrational modes for linear molecules can be calculated using the formula 3n minus 5. The degrees of freedom for nonlinear molecules can be calculated using the formula 3n minus 6, where n is the number of atoms in the entity. Electronic transitions are essentially instantaneous, so there is no time for appreciable motion of the nuclei. So, the transition appear as vertical lines with no change in internuclear distance, which is called as Franck-Condon principle. The Beer-Lambert law governing the amount of radiation transmitted through a sample can be rearranged to give the absorption coefficient of the material synthesized or absorption coefficient of the molecule. These are the concepts we learnt from this lecture. About these concepts, you can learn more by referring some of these websites and other websites available.